Listo. Entonces, bienvenido a esta charla número 10. Ya vamos en la número 10 de Aprende Geotermia, ese programa virtual creado en conjunto, en colaboración entre Geocol y la Universidad de Medellín. Hoy me alegra mucho tener aquí como invitado a Jasmin Raymond. Es profesor del INRS, el Institut National de Recherche Scientifique de Quebec, en Canadá. Antes de hablar más en detalle sobre él, unas informaciones generales. Bueno, le recordamos siempre que el programa requiere apoyo, y no solamente ese programa, sino todo otro tipo de actividades que tenemos como planeadas para la segunda parte de ese semestre. Entonces los invitamos a visitar nuestra página web y si están en condiciones de hacerlo, de registrarse como miembros. Hay opciones para miembro estudiantil, miembros individuales y corporativos para las empresas. La próxima charla, con la próxima charla seguimos en esa misma temática de bombas de calor y geotermia somera, con un invitado desde Suecia, José Acuña. Con él hemos tenido varias conversaciones como a Geocol, intentando como hacer un acercamiento, y ese nuevo proyecto de la UNESCO, GCP 636, del cual también Jasmin hace parte, y así como Mar, que ya habló de la red RIX, y otras charlas que tendremos más adelante dictada por investigadores del SEGA. Son todas charlas de ese ciclo del proyecto IGCP de la UNESCO. Otra información también nueva que les quería compartir, a nombre de Renato Somma, que está aquí conectado con nosotros desde Nápoles, en Italia, y a mi nombre. Somos editores de una edición especial de la revista INRS, de la editorial MDPI. Es una editorial Open Access. Entonces eso implica que los artículos generalmente la revisión es muy cortica, toma por ahí máximo 2 semanas, pero sí hay unos costos de publicación asociados. Es una edición especial sobre energía geotérmica, y unas palabras clave que pueden encontrar con las temáticas específicas en el link en el sitio web que les dejo acá. Entonces, una invitación a todos los grupos de investigación que estén interesados. La fecha límite es en octubre de 2021, entonces hay bastante tiempo para pensar en una publicación en esa edición especial. Perdón. Bueno, el protocolo yo creo que la mayoría ya lo conoce. Entonces después de esa presentación e introducción, Jasmin tendrá más o menos 30 minutos, tenemos 15-20 minutos de preguntas. Los invito a que realicen las preguntas en el chat durante la presentación. Yo voy tomando nota de las preguntas y las realizaremos a Jasmin al final. Pueden hacer las preguntas. Jasmin empezará en español, después pasa a inglés. No importa el idioma, los vamos a ayudar con las preguntas. Entonces pueden escribir tranquilamente en español o en inglés. No hay ningún problema. Bueno, Jasmin, entonces, profesor del INRS, como les estaba contando, desde 2015. Entre sus experiencias quería mencionar, como le comenté, su experiencia en El Salvador con la Geo, porque la Geo es una de las empresas que ha estado más cercana a Geocol, con la cual también tenemos convenio. Siempre nos han apoyado en la Reunión Nacional de Geotermia, y entonces es muy bonito ver cómo ese mundo de la geotermia es muy pequeño. Jasmin estudió en la Universidad de McGill, su pregrado en geología en Montreal, y realizó su maestría y doctorado en la Universidad de Laval, donde realmente nos encontramos, compartimos oficina durante ese posgrado. Entonces fue realmente una experiencia muy linda, y por eso estoy tan feliz de tenerlo aquí hoy. No solamente un compañero de trabajo, sino un amigo muy grande y querido. Realizó 2 postdoctorados el primero en el ETS, en la École de Tecnología Superior en Montreal, y el segundo en el INRS, en el cual después empezó a trabajar como profesor. Es uno de los líderes de geotermia a nivel canadiense y es una persona con recursos muy importantes que comparte con todo el grupo del proyecto de la UNESCO. Y bueno, y eso era lo que tenía más como para decirle, que para mí era lo más importante. Si tenemos todos esos resultados con Jasmin, con su equipo, actualmente hay un estudiante de la Universidad de Medellín que está ya con él en el INRS, María José, otros que han tenido esa experiencia, y todo eso empezó a final de 2014. Aquí estamos en el Nevado de Ruiz, haciendo trabajo de campo con María Isabel, y aunque ya no esté aquí con nosotros, siempre la recordamos. Es parte fundamental de este nuevo proyecto de la UNESCO, recordando las palabras de Jasmin, que me escribió cuando nos aprobaron ese proyecto. Él escribió que parte de eso lo debíamos a ella. Aquí estamos también con su papá, otra persona muy especial que nos acompañó en hacer campo. Entonces, quiero que todo lo que están vinculados en el proyecto de la UNESCO, que han tenido el honor y la posibilidad de conocerla personalmente, siempre la recuerden, porque todo lo que estamos obteniendo es realmente gracias a ella. Con ella se empezó ese acercamiento entre Medellín y Quebec y entre esas dos universidades. Entonces, nada, gracias María Isabel, siempre pienso en ti cuando obtengo un nuevo logro en esa línea de investigación. Bueno, con eso termino y te doy la palabra, Jasmin. Donc, je vais terminer ici. Tu peux partager ton écran.
Ok. Pues muchas gracias, Daniela. Y muchas gracias también a Maria Isabel. She's not here with us today, but I think we own her a lot. And I'm glad, Daniela, that you made this few presentation for voy a hacer mi presentación en inglés o tal vez un poco de español. Puedo hablar un poco español, pero no estoy la mejor persona para hacer la presentación en español con las palabras técnicas. Así que creo que voy a hablar más inglés, pero puedo tal vez ver si puedo tener algunas preguntas en español al final. No sé, tal vez. Do you see my slide correctly?
Yes, I do.
Yes, okay, all right. So I'll start the presentation. My presentation is about ground heat exchangers for geothermal heat pump systems that are used to heat and cool buildings. It's about a small research project we did to improve ground heat exchangers that are installed in borehole to make them more efficient. But by doing this presentation, I'll start with some geothermal heat pump basics. From what I understand, there was a previous presentation about the geothermal heat pump installed near Bogota, so I hope I will not repeat too much. If I do, please stop me and let me know so I can go faster on the general concepts. And if I go too fast on the general concept, also let me know and I can try to explain better what I mean about those geothermal or ground source heat pump system. Actually, different type of geothermal heat pump system. The groundwater at one hand, a heat pump system where we use directly the groundwater for heating and cooling building, and the ground coupled, which are closed loop system. So it's pipe that is buried in the ground either horizontally or vertically into borehole, and which provide the exchange with the ground for efficient heating and cooling. If you want, the open loop system tends to be less expensive and have better performances if we compare the amount of borehole that you need with the closed loop system, right? Just a few borehole in a prolific aquifer can allow to produce a high flow rate of water, and those systems can be very efficient. but they involve a little bit more maintenance and risk. Risk, of clogging the wells, having aquifer that are not permeable enough, or scaling and corrosion of the plate heat exchangers, because in those systems, you never send the water directly into the heat pump. That's what I show on my graph here. The yellow box is an intermediate plate heat exchangers that allow to transfer the energy from the ground to the heat pump, the red box, and then to the building. So the open loop system are a little bit more risk, but more performance, while the closed loop system at the other end are less risk, but tend to be a little bit more expensive. However, in Canada, they are the type of system that are most popular. I think 80% of system are closed loop. And it's because they're pretty much a plug and play solution, right? Since it's a low risk option and you can install this anywhere, right? You don't need a permeable aquifer. You just need enough space to dig trench and install your pipe, or if not, drill some borehole and install in the ground. Well, they tend to be more popular, although the payback period can be a bit longer. In between, there are the surface water heat pump, or in which you take water from a lake or a pond to heat and cool the building, either in an open or closed loop fashion with some coil in the surface water body. But basically, in my talk, we'll discuss mostly the closed loop type, the vertical one, which are more popular for large building as well. The horizontal system are quite popular for residential building, where you have a significant piece of land beside your building, and then you can install these type of system. In a downtown where space is limited, the vertical system tend to be more installed, and they are the system that needs most engineering and design to be operated in optimal conditions. So this slide shows you the operation of the heat pump system in typical, I would say, Canadian conditions. So our ground temperature is near 8 degrees Celsius in southern Canada. The idea is to send inside the pipe a mix of water and antifreeze. So the fluid temperature goes down to below 0 degrees Celsius, but doesn't freeze, right? Because there's a freeze protection down to minus 15 degrees sometime. It's at a colder temperature than the ground. So you extract heat from the ground, and then you recover fluid at 0 degrees Celsius. You extract energy, but it's still a very low temperature, so you need to amplify this energy. So the energy is transferred to the heat pump refrigerant here at the heat exchanger number 1. And then the refrigerant is compressed. So by compressing, you increase the gas pressure, and you have all learned in high school that PV equal energy. So if we increase the gas pressure, that increases the temperature. And you end up with a higher temperature here at number 3, and you can transfer this heat to the air that circulates in your building, and you can heat your building, let's say producing hot air at 31 degrees Celsius to heat the room at 21. So the system needs an input of energy to work. At number 2, it's the compressor, and then number 4, it's the expansion valve to continue the cycle. You need to input some amount of energy. So although we use renewable geothermal energy to operate the system and take that energy from the ground, this geothermal heat pump are more seen as an energy efficiency technology because it will consume some electricity to work. But by doing this, we can save about 60 to 70% of energy we need to heat a building, and about 30–40% of energy for cooling. And I guess the cooling application are probably what are most interesting for you in Colombia. Those systems, they could be revert and operate in different fashion. If you have, let's say, a ground temperature near 10 or 12 degrees Celsius, and the ground maintain its temperature constantly throughout the year, you can send a warmer fluid inside the ground, maybe 15 degrees Celsius, and take the heat from the building and send it back to the ground, such that you cool your building more efficiently. Sorry, I just had a call in my house. I muted the phone. Yeah, system can be both operated heating and cooling mode to ultimately provide energy savings. The performance of the system is highly dependent on the thermal property of the ground, so the thermal conductivity shown by alpha and the heat capacity to lesser extent. And the number of borehole we have is often a function of the ground thermal conductivity and also the borehole thermal resistance, which we will speak with more detail. Typically, these borehole, they have 150 meters in depth. This is a typical depth for borehole in Canada. So it's a relatively shallow system compared to deep geothermal, where we drill kilometer wells. And they are installed in shallow aquifers. In Canada, the geothermal heat pump market is growing. There are more and more systems being installed, and what you see on my map, all those red dots are the systems that were installed and certified in the past by the Canadian Geoexchange Coalition. It's not all the systems that were installed, but it gives you a very good idea of where those systems are being installed, and it's mostly in southern Canada. Where most population lives, from coast to coast, Vancouver on the west coast, then Calgary, Winnipeg, and then the Quebec City to Windsor corridor from southern Ontario all the way to Quebec, the St. Lawrence lowland. This is where most of the population of Canada is located. And this is where they are the most important energy needs, and this is where you find those systems, of course, and a little bit in the maritime. So basically, any geological environment is suitable for a geothermal heat pump system, but some environment will perform better than the other. Most systems are being installed in the province of Ontario, followed by Quebec, BC, Saskatchewan. Ontario is just because this is where most people live and where the heating needs, the energy needs are most important, I would say, generally speaking. And there are roughly, those statistics are a little bit old, but there are roughly 10,000 to 15,000 systems installed in Canada every year. So it's a small industry, but that is growing year after year. Because it has a good potential in terms of energy savings. When the systems are installed to replace either natural gas or furnaces with oil, it helps to reduce greenhouse gases. So there's also contribution for those systems in terms of greening the energy sector in Canada and reducing CO2 emissions. So engineers, geoscientists, when they design those systems, the closed loop system, the idea is to find L, the length of the borehole, the total length of a borehole that you need to fulfill the energy needs of a building, the Qs, okay, that are shown in my equation, taking into account the ground thermal properties and the borehole thermal properties. The ground properties are the thermal resistances of the ground, which depends on the thermal conductivity, actually. And RB is the borehole thermal property, the thermal resistance of the borehole. Considering also at the denominator of my equation, the undisturbed ground temperature and the fluid temperature. So my blue parameter depends on the ground, the thermal state and property of the ground, while the red parameter are design parameter that I can improve to make my system more efficient. The fluid temperature, it's the temperature that I decide in terms of heating mode. The cooler is the temperature, the less efficient is the system, but those systems can have good efficiency working at 0 degrees Celsius, for example, for heating. While in cooling mode, it's the contrary, right? The warmer is the fluid, the less efficient. So it's sort of you have to decide the good balance, right? And have a good fluid temperature in your system that provide energy savings, but that does not increase too much your length, because if the length is too long, then the system is just too expensive to install. So designing a system is really to find a good balance with the, what the ground can give you to fulfill the building energy needs, taking into account what you can change in your design to have more performance from your borehole with the borehole thermal resistance. And the building energy needs, they are represented by heat pulse that are sent to the ground, the Qs, the average heating or cooling load of the year, and of the peak heating or cooling months, that would be January or July, and the peak heating or cooling load, QH. And this equation is good whether it's for a system designed for heating or cooling. And typically, you have about 30% of the length that comes due to monthly and yearly loads, and another 30% that comes due to hourly loads multiplied by the ground resistance, and then another 30% of the hourly loads multiplied by the borehole thermal resistance, such that if you optimize this parameter, RB, you can reduce the bore length by 10, 15, maybe up to 20, 25%. Because at the end, there's always some small resistance, which you have to live with. But there's a way to make those systems cheaper if you change that RB parameter. And that's what we will talk about in this research. Actually, we try to minimize borehole thermal resistance. The borehole thermal resistance, actually, it's a term that describes the ability of ground heat exchangers to resist heat transfer. Heat transfer that takes place, okay, this is a slice of a borehole, and this is my U-pipe in which the fluid circulate, and that would be the ground outside my borehole. So it's the resistance between the fluid and the borehole wall. So it compromises resistance due to flow of water in the pipe that we want to be turbulent to maximize heat transfer, as well as the property and the geometry of the material. So the material that makes the pipe, if it's a single W pipe, coaxial pipe, and how they are disposed inside the heat exchangers, the pipe material, typically HDPE, high density polyethylene, as well as the material that fills the borehole. And typically in Canada, what most people use is grout mixtures, a mix of sand, bentonite, and water to fill in the borehole. And this resistance, which is the inverse of thermal conductivity, right? It's expressed in meters Kelvin per watt. So the inverse of thermal conductivity, well, the smaller the resistance, the better the heat transfer performance is, and the more you can reduce the bore length for a given building, deliver a system that is cheaper to your client and that have a shorter payback period, such that with energy savings, you pay the cost of the system and the user at the end is happy and has an efficient system. Thermal response tests. When we design those systems, we need to know the ground thermal conductivity, right? Because the performance is highly dependent on the ground thermal conductivity. My parameters here, lambda S for the subsurface thermal conductivity. So we do some in-situ tests before building the whole system. Typically, we're gonna drill one well on site. In this well, we're gonna install a ground heat exchanger. So there's gonna be a pipe installed in the well. And sorry, and the well is gonna be backfilled such that we have a pilot ground heat exchanger for our first exploration well that is drilled on site. After the well is drilled on site, a portable unit is brought in the field, And this portable unit is really to simulate the geothermal heat pump operation. So we have, but at a small scale, right, with that single borehole, because, you know, a large system can include tens to hundreds of borehole. And will, you know, depends on the heating, cooling need of the building. But to design the system, we'll just use electric water heater, heat the water, circulate with a pump, measure the flow rate here with a flow meter, and measure the temperature at the inlet and outlet of the ground heat exchangers, and basically evaluate the temperature response. We inject heat in the ground, disturb the thermal equilibrium of the subsurface to infer the thermal conductivity. If you want, this is a bit analogous to a pumping test that is being done in hydrogeology, where we disturb the pressure in the aquifer to evaluate the hydraulic conductivity. Then it's the same thing. We change the temperature of the ground by injecting heat, and by monitoring the temperature response, we identify the thermal conductivity. So we use this equation. This is the infinite line source equation. This, for those that are familiar with hydrogeology, is the same thing as Theis equation. Actually, Theis equation was derived from the infinite line source equation, and we could do the analogy between heat transfer and groundwater flow, Fourier's law and Darcy's law. But basically, it's the same equation here. We evaluate the average ground temperature based on the undisturbed ground temperature, the heat injection rate, Q, multiplied by what would be in a pumping test, the well function, if you want. Multiplied by a term that depends on thermal conductivity and the well function. That depends on the borehole radius and thermal diffusivity of the ground. This part of the equation, what it gives you is the temperature at the borehole wall. To link the temperature at the borehole wall to the fluid temperature, what we're interested, we need to add the effect of the borehole thermal resistance in the equation. So by monitoring the temperature in the thermal response test, I can obtain two things: the ground thermal conductivity and the borehole thermal resistance. But often those two parameters are connected and they are dependent on each other. So we have to find ways, right? There could be more than different solution of thermal conductivity and borehole thermal resistance that will fit the thermal response. So we have to find ways to distinguish the effect of both parameters. So the idea to reduce ground heat exchangers, it's really to reduce borehole length. Typically, the thermal resistance of a ground heat exchanger vary from about 0.05 meters Kelvin per watt. This is a very small resistance, to 0.35 meters Kelvin per watt. This is a very high resistance. And by changing this, well, you have an effect on the length of GHE. 40% would be, well, a very large effect, you know, if you consider those kind of resistance. But in a real system, I mean, it's always smaller than this. Well, 0.05, it's a fairly low number that we wish to achieve for efficient heat transfer. Typical design for ground heat exchangers, at least for borehole we install in Canada. I'm not sure in Colombia for the system they are, how they were designed and installed. But typically it's a 6-inch diameter borehole or a 15 centimeter if you prefer, that are drilled with rotary drilling technology. The depth is about 150 meter, 500 foot roughly, and you can install, well, most of the time what is being installed is a single U-pipe to flow the fluid that makes the heat transfer with the ground. But there are alternative design, coaxial pipe, a large pipe, install a small pipe and flow inside, but this is more complicated to install in the field and drillers don't like this. Other option is the double U-pipe. So instead of having a single U-pipe, you have a double U-pipe, more pipe area that allows you a greater heat exchange. Also more fluid inside the borehole, so a thermal mass of water that can impact the performance of the system with more heat storage capacity in the borehole. The borehole is often sealed with grout. The idea of the grout is to protect the borehole to have either surface water infiltration or infiltration of different groundwater levels that could be intercepted by the borehole. So to protect the groundwater resources and aquifer, the boreholes are grouted, but also the grout is there to ensure the thermal contact. The grout actually is made of a mix of water, bentonite, and sand. The idea of using the bentonite when mixed with water, it's inflate, and it's a low hydraulic conductivity material that presents flow, but it also has a very low thermal conductivity, just 0.7 watt per meters Kelvin. So in the mix, we add sand, quartz sand, that have a high thermal conductivity and can help improve heat transfer. But you need to balance not to have too much sand, right? Other type of material that have been used for thermal conductivity enhancement is graphite. Graphite that have a very high thermal conductivity when it's parallel to the flakes. But graphite remain expensive and is not commonly used for ground heat exchangers, although it have an interesting capacity to increase thermal conductivity. But sometimes it is being used. And then the pipe that makes the heat exchangers, typically it's a high density polyethylene. You see the thermal conductivity of this pipe is very low, 0.4 to 0.7 when it is enhanced with carbon type nanoparticle for a pipe that is specifically designed for geothermal heat pump system, but most of the time it's just HDPE, regular 0.4 watt per meters Kelvin. This is a very low, this is a plastic pipe that is actually an insulator. So it's the weakest part of the well, we could say, in terms of heat transfer. And the reason why people are using plastic pipe is because they're very robust, and the pipe can last a long time in the ground without being affected by corrosion, but it's not ideal in terms of heat transfer. So what we've done at INRS is try to improve those ground heat exchangers with a pilot test site that we have at our lab facility. We have a site with different heat exchangers, a conventional double U-pipe and a double U-pipe ground heat exchangers, unconventional, and a conventional single U-pipe, and also some observation well in between to monitor the ground when we do test. This is basically the stratigraphy that we have at the site. It's not a very ideal site for geothermal heat pump system, although this building that is shown here is heat and cooled with geothermal heat pumps, and the ground heat exchangers are under this parking lot. But the ground, it's more or less 10 to 15 meters of overburden, silty overburden, followed by actually a shell that don't have a very high thermal conductivity, so they're not ideal for heat exchange, but that's the ground we have, and it's fine for geothermal heat pump system. One of the hole is single U-pipe versus this one is double U-pipe, a little bit deeper, 160 meter versus 153 meter. So the ground heat exchangers with the single U-pipe was installed as a first research test. We wanted to verify what was the impact of borehole with a smaller diameter. Actually here it's not the 6-inch, but 4.5 inch, so 114 millimeters in diameter. And we had a drilling contractor that came on site and that proposed these borehole with a smaller diameter and wanted to see what was the effect on the borehole thermal resistance. So we installed this single U-pipe grouted borehole. Thermal conductivity of the grout is 1.7 watt per meters Kelvin. It's typical thermal conductivity of the bentonite sand mix, regular HDPE. No space clip. Sometimes we put space clip to have the pipe spread apart to decrease thermal short circuiting. In this case, there was no space clip installed. So after installing this ground heat exchangers, we bring in the field a thermal response test unit. This is a thermal response test unit of industrial partner, Energiestat, that have an interesting unit that we can control remotely through the cloud. once everything is connected, of course. And what is nice, yeah, about this unit is yeah, that you can actually sit in your office and control the heat injection rate. So that's the test we perform, about 80 hours of heat injection. You see the average temperature inside the borehole increase. And then after 80 hours, we stop heat injection, but we kept circulating fluid in the ground and the temperature slowly decreased. And with our light source model, we tried to fit the observed temperature. There was some small variation in the heat injection rate that were due to atmospheric temperature changes, although the pipes were well insulated. So we consider variable heat injection rate in the analysis of this test using the temporal superposition principle. And what we found out was a ground thermal conductivity of 1.75 watt per meters Kelvin, so it's not very high value. A good value would be above 2.5 watt per meters Kelvin, but that's basically what shells from sedimentary basin gives you. And a borehole thermal resistance of 0.088 meters Kelvin per watt. That's an interesting value, I think. I would say average value. That is characteristic of single U-type U-shaped borehole. Similar borehole with a 6-inch diameter would have a slightly higher value, near 0.1 meters Kelvin per watt. So the smaller diameter allowed to reduce a little bit the thermal resistance, but it's pretty much, you know, average value that you can have for these kind of systems. Then with our second ground heat exchangers, what we did is we tried to improve the system with a W pipe, and instead of using grout, the pipe was just laying in the groundwater filling the borehole. There's actually no grout. In this setting, okay, the bedrock, it's shale, very low permeability. There's not really aquifer and groundwater resource to protect. So we think in this situation, it's okay not to use grout. The top of the borehole is sealed with the sealing outside of the casing, not shown here. So we prevent infiltration of surface water, but after that, it's all groundwater flooding the borehole. And the thing that is interesting is when you inject heat, there can be some natural convection movement. So although the water has a very low thermal conductivity, 0.6 watt per meters Kelvin, when you bring heat in the pipe and then this heat is transferred to water, there's some natural convection movement. And then this convection helps to decrease the, to dissipate the heat. So then you start to have some better heat transfer toward the subsurface. So in this case, the pipe also was a thermally enhanced pipe. So it's HDPE mixed with carbon type nanoparticle that increased the thermal conductivity of the pipe. So same thing again, thermal response test was done, bringing this field test unit with the heater in the element, insulating carefully the pipe again, even more than the previous time, learning from our previous mistake. This test was done in the winter. This is just the beginning of the test with the beginning of the winter, but it was finished by the end of January, where there was about 1 meter of snow on the site. So we tried to insulate everything carefully. And actually what we did is different tests, okay, with different steps. Here you see a first heat injection until 75 hours at heat injection rate of 27 watt per meters during 63 hours. Then until 108 hours, we increase a little bit the heat injection rate, but decrease the flow rate by by 2 about. So the flow was less important, while here it was more important. And we stop heat injection, allow the borehole to recover. So that's the 1C period until 323 hours, where, well, each injection rate is actually negative. It was just because the temperature was cold at surface. But flow rate also is reduced, but it kept flowing inside the borehole. And then Here we pick up again with higher heat injection rate, 30 watts per meter, but a flow rate that is similar to our 1B case, and a thermal recovery period at the end. And the reason why we did this is that we wanted to see what's the impact of changing the flow rate and changing the heat injection rate. Analysis of this test fitting observed temperature with compute temperature using the line source model give us a ground thermal conductivity of 1.74 watt per meters Kelvin. So it's pretty much the same thing as what we had previously for our other borehole that is close to this site. So it's good, our test is reliable. But in terms of borehole thermal resistance, the results are quite interesting. For a high flow rate and a low heat injection rate, we get 0.05 meters Kelvin per watt. And this is what is shown on my graph here. You have the borehole thermal resistance as function of flow and as function of the heat injection rate. For a low flow rate and a low heat injection rate, the borehole thermal resistance increase. And for a low flow rate and a high heat injection rate, the borehole thermal resistance decrease, but not as much as when there's a high flow rate. So for these boreholes, okay, that are made with groundwater filling the hole, it's already known that if you change the heat injection rate, that affects the borehole thermal resistance, because the more heat you inject, the more convection, natural convection you get in the ground, and the lower goes the borehole thermal resistance. But the impact of flow rate is a little bit unknown, and that's something we demonstrated here. The flow that you assume have even more impact on the borehole, not that you assume, but the flow that you set have even more impact on the borehole thermal resistance than actually the heat injection rate. So those systems, I think, with open hole and water, groundwater filling the hole, has a good potential, especially for cooling. Because in cooling mode, for systems that you would expect in Colombia, for example, well, you're going to inject heat in the ground and you're going to start to have free convection in your borehole. So that's good. But those systems need to be operated at a high flow rate that decrease the thermal short circuiting. The flow rate have an impact on the thermal short circuiting in between the pipes, and the higher the flow, the lower is this thermal short circuiting, and the lower you can decrease your borehole thermal resistance to actually have an impact on your borehole length needed for your system. So this concludes my talk. The idea, maybe the take-home messages, is that system, geothermal heat pump system, can be improved and better designed by minimizing the borehole thermal resistance. There are different alternatives for doing this, and groundwater-filled boreholes are one of the interesting options to look at, although they're not very common right now in the industry. But I believe it's something that should be more and more used, especially for systems that are designed for cooling purposes, which I guess would be the case for your system in Colombia. And one of the key in designing those systems is look at the flow rate, which have an important impact on the borehole thermal resistance. Thank you. I guess this concludes my talks.
Muchas gracias, Jasmin. Muy bueno de volver a escuchar todas tus experiencias y trabajos que han podido hacer ahí en Quebec. Hay dos preguntas que nos hace la misma persona. Nelson Molina nos dice, te pregunta, do you take into account the groundwater flow conditions to size the ground loop? Esa es la primera, y después te hago la otra.
This is very rarely done. It can be done. There are ways to take this into account. And I think that when there is some important groundwater flow, it has to be taken into account. But typically, engineers that design those systems, they rely on basically solution for conductive heat transfer in the ground, and they neglect the groundwater flow. But there are alternatives like the moving line source, infinite line source solution that could be used, and the line source move with the speed of groundwater, for example, or a numerical model like FEFlow that allow you to model heat conduction and advection in the ground. This is a little bit more complex, but it can be done. And when there's important groundwater flow, this can help to either dissipate heat or cold in the ground and improve the system performances. I have been involved in a follow-up of a system that was installed for a school that was 1 kilometer away from a quarry where the groundwater was pumped. And at the site, the groundwater flow was quite important and had a lot of impact on the system performance. And people at the school were scared that the quarry would stop operating and pumping, and that would decrease their performance. So in some time, yes, it is important, although it's not commonly done by the industry.
Ok, gracias. La otra de la misma persona pregunta, for the TRT, can you use an analytical solution that considers the groundwater flow?
Yes, well, the analytical solution, which I mentioned in my previous answer, the moving infinite line source equation. The idea is to use the same equation, the infinite line source equation, but you assume spatial superposition of your heat source, and you move the heat source according to the speed of groundwater flow. This is a solution that is available and is well documented in the scientific literature. However, I haven't seen that solution yet in the commercial software that people use to design and system and analyze thermal response tests. So it's possible, but maybe some development are still needed to make it easy accessible to most practitioners.
Listo. Seguimos con otra pregunta de Fermín Carrillo. Bueno, te dice, very good presentation, Jasmin. Can you explain what are the advances on ground thermal energy storage? Is this feasible with different wellbore configurations?
Yeah, interesting question. Yeah, thermal energy storage is a different topic. What I show you here, it's more geothermal heating, right? Either taking heat from the ground or injecting heat just to heat and cool the building. Underground thermal energy storage, the idea is to take excess heat and store it in the ground, increase the ground temperature, and retrieve this heat later on when you need it, right? For example, in Canada, during the summer, we have a lot of sun, and we can produce solar energy, but there's no need for this solar energy because the heating needs are mostly in winter. So some system has been designed, and there have been some pilot system operation. I am especially thinking about the Okotoks project we had in Drake Landing Solar Community in Canada near Edmonton in Alberta. That's one of the most advanced projects, I think, on thermal energy storage, where solar panels were used to create a heat store in the ground and then retrieve this heat and heat buildings. In those kind of systems, you can expect about 50–40% of heat loss in the ground, but still, yes, you can recover by having a tight bundle of ground heat exchangers. In the regular geothermal heat pump system, you want your borehole to be far apart from each other, so there is no thermal interference, while for thermal energy storage, you want the borehole to be closely spaced together. So actually, you inject heat at the middle and you recover by the sides. Those systems works, but are fairly expensive to install. So right now, they're more used, I think, on the experimental basis, with some demonstration project and initial commercial project, but we're far from having, I think, important industry and many systems regularly installed. On my research team, we're interested in this topic, and we've actually been working with remote and northern communities that live in Arctic and subarctic climate. And we do some work to see if we can use solar panels in the summer that last, the days in the summer are very, very long, but the summer period is short. So we try to produce heat in the summer and retrieve it for the winter to heat buildings. So yes, I would say to answer it short, yes, it's possible. And there's some research to do to make it more economical.
Listo, perfecto, muchas gracias. Ahora una pregunta de Mar, de Argentina. Te pregunta si los instaladores en Canadá son flexibles para adaptarse a estas propuestas. ¿No está más restringido por la legislación?
The answer is no. Installators are not very flexible. Typically installer or drilling companies and they
Jasmin, Anastan, s'il te plaît, Mar agregó un pedacito. Está más restringido a rellenar the borehole with water, la perforación con agua. Hay problemas con eso.
There's two things. There's the drillers that want to do their job, right? And wants to have a simple job. And when you come up with some innovation, you have to change things, and it's very long to change the process. But slowly we're getting there. And there's the regulation aspects, which I guess was the art of the question, right? Can we do this because of groundwater regulation to protect groundwater resources? In our regulation that we have in the province of Quebec, because regulations are different from province to province, yes, this is allowed as long as you show that you don't cause a threat to groundwater resources. So if you were to install this in a ground that there are some known aquifer and the aquifer is used for drinking purposes, that would probably not be the best option to install. But if you're in a subsurface that are made of shell, like I showed at our experimental lab, and that there are basically very little or no groundwater resources, then you are allowed to do this as long as you seal the top part of the borehole and you prevent the surface water to infiltrate. But groundwater protection is an important issue. Right now, the legislation is flexible enough, but it's not type of system that are often installed because you need an expertise, right, from the ground point of view to make sure there's no risk. And often the system, people in the building sector, they like plug and play solution, and they want safe and simple solution, even though it's more expensive. And that's why most systems are just closed loop with borehole filled with grout. But for larger system, where you can pay a groundwater scientist and have some groundwater expertise and evaluate the risk, and if the risks are fair or little, then you can move forward with this type of installation.
Listo. Ahora hay una pregunta de Iván Osorio. Hola, es desde REN, ¿cierto? Es un colombiano que trabaja con Tanguy. Sí, es él. Si no, si no hay otra persona con mismo nombre y apellido. ¿Me confirmas, por favor, para saber si estoy hablando con la persona que pienso? Ah, bueno, listo.
Parte de la familia.
Sí, esto. Pregunta si, bueno, did you estimate Reynolds numbers in your different tests? Is the flow regime, the regime de flux, turbulent in your YouTube exchangers?
Yes, we did. I don't have the number on top of my head. Of course, if I go back to some of my slides, you see the flow rate change a lot, from 4 times 10 to the minus 4 meters second to 2 times 10 to the minus 4 meters second. In both cases, it was turbulent flow. But for the case 1B, it's like transitional turbulent, while 1A, it's fully turbulent flow. So the turbulent flow is, of course, better, and that's why we get a smaller borehole thermal resistance. But I'm sorry, I don't remember the exact Reynolds number on top of my head.
Okay. Si alguien tiene más preguntas, tenemos todavía 2 minuticos. Si no, mientras, bueno, Marte saluda, no sé si está leyendo la chat, Jasmin. Ahí todo el grupo de RENAC. Sí,
maybe I should.
No, entonces, bueno, muchas gracias. Sí, otra preguntita. Bueno. Bueno, esa es larga, espérame. Entonces, Fernando Rivas nos escribes, one of the most expensive parts of a heat pump system is the heat exchanger. Entonces, la primera pregunta, are there other options to reduce the size of the heat exchanger without affecting the COP?
Well, the point is good, right? The ground heat exchangers is the most expensive part, and there are various options. And the idea is to try to have an option that allow the best heat transfer with very little, less borehole thermal resistance, so that you have the same operating temperature and you don't have any impact on COP. What I showed are options to have a groundwater-filled borehole. Other options that have been tried are to use a coaxial pipe, which have a large diameter and more fluid and actually less grout, sometimes even no grout, or use those borehole in standing column well. Actually, it's an open loop system, but you have a central pipe and you just circulate the groundwater as a heat exchangers. Those are all different alternatives that can be tried to reduce the borehole thermal resistance and make the system better in terms of heat transfer performance and have a similar COP for your systems. But there's no simple solution, I would say. The coaxial pipe, it's interesting, but it's difficult to install in the field, so it's not used that much. W pipe could be something is something interesting, and it's not that difficult. So I think there will be more and more of those systems installed. Then the other option, what we have to look at, and this is the next step where research is going to move, it's not to improve actually the borehole performance, because in terms of borehole, I think lots of research has been done and we're getting on the right track, but it's the next research where I think we'll look at to how to improve the ground. How can I, let's say, induce some pumping and activate groundwater flow so I have a better heat transfer performances? Question that people are asking now is in those groundwater-filled borehole, can I put a pump inside and start pumping groundwater? So I have a natural, I have an artificial flow of groundwater that helped me to increase the performance of the system to ultimately decrease ground heat exchanger size. So those are the things to look at for the future.
Okay, gracias, Jasmin. There are still 3 questions. Yeah. Do you have a few minutes more?
Yeah, okay. I have time, no problem. I see many questions on the chat. It's a pleasure to answer. So if people want to stay, we can go for it.
So the second one from the same person is, why has the use of nanofluids or nanomaterial not been exploited? Do you have any experience?
No experience on this. We've worked with nanoparticle to increase the pipe thermal conductivity. But for the fluids, I don't think it hasn't been used. And that's, something interesting to look at. Honestly, I'm a very bad chemist, and I'm not sure how to start with this, but yes, that could be an interesting thing to look at. Improve the thermal conductivity of the fluid with nanoparticles. Yes.
Okay, and the last one from Fernando, I don't remember the name. Yes. Is in Canada, do you have support from the government to install heat pumps as they do in the USA?
Yes, we do. It depends on provinces and on governments. Sometimes government put some program and then they go away and the program go away with the government. And it changed from years to years, but basically we do have support for the residential sector. but also we have some support for the commercial and industrial sector through energy efficiency programs, at least in the province of Quebec, where I do most of my work.
Okay. The next question, is there any research ongoing on the performance of borehole ground grids as opposed to single well systems?
Yes, there are quite a lot on that topic. I would say that researchers, colleagues from Montreal Polytechnique or ETS, where I've worked in the past, have done much more work than me. But yes, there could be interaction in between the borehole, right? And you want, well, if it's a conventional system, you want to minimize this. And all this become to the G function that describe the thermal response of the borehole. And there have been lots of research try to better define those thermal response with G function and try to make sure the thermal interaction in between the borehole is as smallest as possible, so your field is more efficient for regular system, while for thermal energy storage, the contrary, to have more tight boreholes, so you can recover all the heat that is injected in the ground.
Ok, yo creo que esa concluye las preguntas, que bueno, gracias a los que nos agradecen por eso, bueno, traducciones simultáneas miraremos, sí, yo entiendo, miraremos para el futuro, sobre todo con respecto al proyecto de la UNESCO, si queremos hacer algo, como hay tantos países, es tal vez un elemento que vamos a analizar, y bueno, les recuerdo el próximo webinar el viernes por José Acuña del KTH de Suecia. Entonces nos va a dar como la visión, como en Europa, la experiencia que tienen en Europa y otro país que utiliza mucho esos sistemas de bombas de calor acopladas al subsuelo. Y esos videos los encontrarán en el canal de YouTube de Agiocol. Y bueno, creo que no falta nada. Muchas gracias a todos por la asistencia y nos volvemos a ver el viernes a las 2 de la tarde. Gracias, Jasmin, de nuevo.
Well, thanks a lot. Fue un placer de hacer esta presentación. And if there is ever some interest to install some geothermal heat pump in Colombia and do some research about this, I'm always happy to share our experience and transfer expertise toward South America. It's a pleasure for me to do this.
Ok, perfecto. Muchas gracias a todos. Feliz tarde, noche, según donde estén.
Muchas gracias.
Chao, Jasmin.
Bye-bye.